This video is going to show you how to do calculations with common ions. So the first thing we're going to do here is we are to calculate the H plus and percent dissociation of hydrogen fluoride in a solution containing 1 molar hydrogen fluoride and 1 molar sodium fluoride. So the first thing that you want to do is you want to write the dissociation reaction for the weak acid or base, because remember the salt is being added to it. So I will write HF. Because it's an acid, I can put water there or not. I'm going to do it in this case. The acid will donate a proton to the water, and I will get fluoride ion and hydronium ion. I'm going to set up an ice chart, and then water is not going to be included because it is a pure liquid. So now what I want to do is I'm going to substitute what I know. So if I look, I have 1 molar hydrogen fluoride, and then if I think about my sodium fluoride, that completely dissociates. So if I have 1 molar sodium fluoride, I will also have 1 molar sodium ion and 1 molar fluoride ion. So this would be 1 molar fluoride. And before this comes to equilibrium, I have no hydronium ions. So initially when these two are mixed, I have nothing here. Okay. So now what I'm going to do is, because I know my Ka, I could write my expression. So it would be concentration of fluoride ion times concentration of hydronium ion divided by the concentration of hydrogen fluoride. My Ka is 7.2 times 10 to the negative fourth. Because I have this, I can use x. So this side has a 0. Equilibrium will shift to the side with the 0. So product side is plus x, reactant side is minus x. So I have 1 minus x, 1 plus x, and x. So in the numerator, I will have x times 1 plus x, and then I will have 1 minus x in the denominator. Now, sometimes I will be able to approximate, and sometimes I won't be able to approximate. But I want to check that because my math can get kind of complicated if I don't. If I take Ka times 100, so if I take this 7.2 times 10 to the negative fourth, I am going to get 7.2 times 10 to the negative 2, which is really 0.07212. That number is still less than or equal to my initial acid concentration. So that tells me that it's okay to approximate. So I'm going to go ahead and approximate. So what that means is that the x's that are added on or subtracted off of this number are so small that because of significant figures, these are essentially going to be 1. So this x is 0 and this x is 0. So what I really have is 7.2 times 10 to the negative fourth equals x times 1, which would be x over 1. So because this is over 1, my x is really equal to 7.2 times 10 to the negative fourth. Okay, so what does that tell me? That tells me I could calculate my fluoride ion concentration. I could calculate my hydrogen fluoride concentration at equilibrium. And that also gives me my hydronium ion concentration. So what they asked me to do is calculate hydrogen ion concentration. That's what I've got here. I want to identify that. So I'm going to say that is equal to hydronium ion. Because it's a concentration, I need molarity. And then we also need percent dissociation. So to do percent dissociation, we take the concentration of hydronium ion, so 7.2 times 10 to the negative fourth. We are going to divide that by our initial acid concentration, which is 1 times 100. So our percent dissociation is 0.072%. Now, you probably, wait, I think I did my math wrong. Nope, that's right. Okay, so what I want to do is I want to compare this to what we would get if we didn't have the common ion. So what I want to do is I'm going to go back and I'm going to get rid of everything that we did that I don't need. So let's get rid of all of this. Hope it goes away. Okay. Now let's imagine that all we've got, let's say we don't have any sodium fluoride that we have added. So we just have 1 molar hydrofluoric acid. So 1 molar, we would have 0 of each of these if we didn't have a common ion. Our equilibrium expression would still be the same. Our Ka would still be the same. But this time, well, the initial shift would still be the same because it goes to the side with the 0. This would be 1 minus x, x, and x. So we would have x squared equals 1 minus x. The approximation is still going to stay the same. That's not going to change. So really, this is going to be 0, so I can get rid of it. So my x squared, because I have a 1 in the denominator, is equal to 7.2 times 10 to the negative fourth. So if I take the square root of that, 7.2 times 10 to the negative fourth, we get 2.7 times 10 to the negative 2 molar, and that would be for our hydronium ion concentration. So let's calculate percent dissociation for this so we can compare. So if I do this up here, this is without a common ion. So our percent dissociation is 2.7 times 10 to the negative 2 divided by 1 times 100. So that really, when I do the math, is 2.7% dissociated. Okay, so without the common ion, hydrofluoric acid is 2.7% dissociated. When we added the common ion, so this would have been 1.0 molar, what happened is the equilibrium shifted to the left, which would mean we would have less, or concentration of each of these would decrease. And we saw that because with the addition of the common ion, our percent dissociation was only 0.072%, which is much lower than this. Okay, I want to do 2 more examples. Okay, in this situation, you're going to calculate the pH. So we're looking for pH of a solution containing nitrous acid. So nitrous is HNO2. Let's do this one without water. So that will dissociate into H plus and NO2 minus. I'm going to create an ice chart and I'm going to fill in what I know. So I have 0.085 molar nitrous acid and 0.10 molar potassium nitrite. Well, that's potassium nitrite, KNO2. We know that this is going to 100% dissociate. So if this were 1 molar, each of these would be 1 molar. but this is 1.0 molar. So I'm sorry, it's 0.10 molar. So each of these is 0.10 molar. And nitrite is the ion that's common. So that will be 0.10 molar. I don't have any H plus when I put this in there initially. If I write my expression, I will have Ka is going to equal H plus concentration times nitrite concentration divided by nitrous acid concentration. I know that my Ka is 4.5 times 10 to the negative fourth. This reaction will go in the direction of the zero. So the product side will go up by x. The reactant side will go down by x. I will get 0.085 minus x, x, and 0.10 plus x. Don't forget that you've got something here. So when I substitute, I'm going to have x times 0.10 plus x divided by 0.085 minus x. Okay, I'm going to check and see if I can approximate. So if I take my Ka, which is 4.5 times 10 to the negative fourth, if I multiply it by 100, I get 4.5 times 10 to the negative 2, which is 0.045. If I compare this to this, 0.045 is still smaller than this is, my initial concentration. So I can approximate, although it's kind of close, so if you wanted to do the quadratic, you could. That will make this x0 and this x0. So we will have, let's change colors, 4.5 times 10 to the negative fourth equals 0.10x divided by 0.085. Okay, so I'm going to take 4.5 times 10 to the negative fourth times 0.085, and I get 3.825 times 10 to the negative fifth. That equals 0.10x. I am going to divide both sides by 0.10. That gives me, let's do sig figs, 0.38 times 10 to the negative fourth molar. So that's our concentration of hydrogen ion. So now it has asked me to calculate pH. So pH is equal to the negative log of our hydrogen ion concentration, which is this down here. So negative log of 3.8 times 10 to the negative fourth. And I have 2 sig figs, so that tells me 2 numbers after the decimal, so 3.42 is the pH of that solution. Okay, one more example. This is with a weak base. Okay, so as I read this, I've got 0.10 mole of ammonium chloride. Okay, ammonium chloride is my salt. That dissociates completely. So if I have 0.10 mole here, I will have 0.10 mole of each of these 2 ions. As I read, I've got ammonia. That's my weak base. So I'm going to write the dissociation reaction with my weak base plus water. In equilibrium, bases will accept protons. That gives me ammonium and hydroxide. If I look up here, I have ammonium right here, and I have ammonium here, so ammonium's my common ion. Set up an ice chart. I'm not including water because it's a pure liquid, and I'm going to substitute what I know. What's different here is these are in moles. So I've got 0.12 moles of ammonia, and I was nice to you. I gave you 1 liter of solution. And then ammonium chloride, I have 0.10 moles of ammonium in 1 liter of solution. No hydroxide before these, before the moles of each of these are mixed. So this product side is my 0. That will go up by X. Reactant side goes down by X. I have 0.12 minus X, 0.10 plus X, and X. So now I write my KB expression, or my equilibrium expression, ammonium times hydroxide ion concentration divided by ammonia concentration. I look for the KB of ammonia, and that is 1.8 times 10 to the negative fifth, pretty small. Ammonium is 0.10 plus X. Hydroxide is X. Ammonia is 0.12 minus X. Okay, if I take Ka times 100, I get 1.8 times 10 to the negative third, which is smaller than these, so it's okay to approximate. I will make the X's that are added on or subtracted off 0. I don't want to make this X 0. So what I get is 1.8 times 10 to the negative fifth equals 0.10x divided by 0.12. So 1.8 times 10 to the negative fifth times 0.12 gives us, let's change color, let's do yellow, 2.16 times 10 to the negative sixth equals 0.1x. Dividing both sides by 0.1 gives us 2.16 times 10 to the negative fifth molar is X, which is my hydroxide ion concentration. Now I could calculate percent dissociation, I could calculate concentrations of reactants or products, but that's not what it wants. I'm going to get rid of this. So I've got hydroxide ion concentration. I want to go ahead and I want to use hydrogen ion concentration is equal to 1 times 10 to the negative 14th divided by my hydroxide ion concentration, 2.16 times 10 to the negative fifth. And when I do that, I get sig figs, let's do 2, 4.6 times 10 to the negative 10th molar for hydrogen ion concentration. If I do pH equals the negative log of 4.6 times 10 to the negative 10th. This is bad. I tell you guys not to write all over your paper, and look at what I'm doing here. I will get a pH of, okay, 2 sig figs, because I have 2 here and 2 here, so I do 2 numbers after the decimal, a pH of 9.33.